Hi, my name is Jane, and I'm a PhD student in the computer science department at Yale. And today I'll be talking about our work on efficient statistics with unknown truncation, polynomial time algorithms beyond Gaussians. This is a joint work with my wonderful collaborators, Anay, who's a fellow PhD student at Yale, and Manolis, who is our advisor. To give an idea of the problem that we're solving and its potential applications, let's look at this very simple stylized example. Let's say you are the founder of a new mobile device company and you've decided to pilot your product to a limited group of users. Let's say limited to this particular geographic region or neighborhood within a big city. Now, you haven't observed the data of some people outside of this pilot program, but now when you're deciding where to station additional resources when you expand beyond the pilot, you might want to ask some questions about the general population of users. For instance, let's say we make the assumption that the people are distributed according to some Gaussian distribution, and you want to figure out where they are most concentrated, for instance, around the mean of this distribution. Without truncation, the true mean might actually lie somewhere here, but we haven't observed the data point of the people to the right of this arbitrarily drawn boundary. Instead, if we calculate the mean using the data that we have available, we might actually see that the mean is over here. In general, truncation and censoring, where in censoring you also observe the count of data points hidden from you, are common due to many reasons. These can come from limitations of measurement devices or limitations of data collection methods themselves, for instance, due to legal or privacy constraints. As one can imagine, these missing data problems and systematically missing data arise in a plethora of applications, such as in physics, economics, clinical studies, and social sciences. As a concrete example, this type of truncated data happens a lot in astronomy, for instance, in this problem of quasar detection. Quasars are these highly luminous and beam-like stellar objects that are powered by supermassive black holes in the middle. So despite being very luminous, these quasars are very hard to detect. One may want to answer some questions about the properties of these quasars. For instance, were older quasars brighter? To answer this question, if you had full information, one might want to plot the redshift on one axis. This redshift is a proxy for the age or the distance of the stellar object from us against its apparent luminosity, and maybe run some correlation analysis there. But in practice, we don't have this full information, and truncation happens for a variety of reasons. One, on the bottom end of this luminosity scale, redshifts of dim quasars are hard to measure. On the other hand, on the upper end of this luminosity scale, bright quasars can be confused with stars and galaxies. In both cases, astronomers tend to drop this data. Furthermore, observing quasars is costly, and so the available data is often incomplete, in the sense that the data that we have may be a patchwork from different observational surveys, but missing data can just come from the fact that these different parts of the sky were not observed. The point that I'm making here in this example is that the survival set can be very complicated, and we might not know exactly what it should be. Now that we've seen some examples, we can abstract out some of these ideas to describe a problem setting. So we're going to assume that a distribution comes from some distribution family parameterized by this parameter theta. And here we're going to consider the exponential family of distributions. For those who have seen it, this family of distribution captures a lot of famous named distributions, which include Gaussian distributions, exponential distributions, and Weibull distributions, and many, many more. There's also going to be a true parameter theta star, so that the density parameterized by this theta star is the true data generating distribution. However, instead of observing everything from this distribution, there's going to be an unknown survival set, and only points in this unknown survival set is what we observe. We also require that this unknown survival set has at least constant probability mass under the true data generating distribution. So in other words, Truncation is when we observe samples from this true data generating distribution conditioned on the sample being inside this unknown survival set. So as an example here on the left, let's say our true data generating distribution is standard Gaussian. After we truncate it to, say, an interval 0, 1, we observe the distribution on the right. Our goal here is from truncated samples on the right, find a parameter theta so that it is close to the true parameter theta star, or in other words, find a distribution parameterized by this theta such that the TV distance between this and the true data generating distribution is small without knowing the truncation set S star. We're going to be focusing in this high dimensional setting where the dimension of X, which is D, and the dimension of the parameter theta, which is M, could be much bigger than the inverse accuracy parameter. And so, as I kind of mentioned earlier, if you don't do anything clever and you just take the empirical mean and variance of your truncated data, you might fit a Gaussian like the one on the right. And as you can see, this is very different than the true data generating distribution. So you need to do something else, something more clever. This notion of statistical estimation with truncated data is not new and in fact has a very long history of statistics. So even in the early days in the work of Galton, Pearson, and Fisher, we had methods for statistical estimation with truncated data. However, a lot of the time in these early works, these methods work in these low dimensional regimes, which become computationally inefficient algorithms in high dimensional settings. In addition, they often use very explicit knowledge of the truncation set. So in 2018, Daskalakis, Gouliakis, Amos, and Zampetakis had this first polynomial time result for learning the parameters of multivariate Gaussians in this high dimensional regime, but with some minor access to this truncation set S, which is this membership oracle. So a membership oracle just tells you whether a point lies inside this S or not. Then in 2023, I, with Wibizona and Zampetakis, generalized this to exponential families. And in these works, the approach is to use a projected stochastic gradient descent procedure to optimize a population likelihood. And we get around calculating these normalizing constants by rejection sampling via this membership oracle access to S. As far as results on estimation with unknown truncation, so not even this membership oracle access to S, one of the only works is this one in 2019 by Kantonis, Samos, and Zampetakis, which learns the parameters of certain restricted Gaussian distributions, those with diagonal covariance matrices. And this algorithm takes time d to the polynomial in Gaussian surface area of the set over epsilon. So Gaussian surface area is some measure of complexity of the set S. Also, due to a recent result earlier this year by Diakonikolas and others, says that any SQ algorithm needs at least this much time. And in fact, even if they have other intersections of having finite VC dimension and bounded Gaussian surface area, we can't get around this lower bound. So naturally, two questions come up. The first, following up on this 2019 paper, is can general Gaussians, so not just those with diagonal covariance matrices, just any Gaussian be estimated with unknown truncation set? Furthermore, is this possible beyond Gaussian distributions? The second, addressing this lower bound, is can we have polynomial time algorithms given that we put even more restrictions on this unknown truncation set? For instance, half spaces or other simple sets. Our paper addresses both of these questions. Now I'll be talking about our main results. And for ease of exposition, I'm going to be focusing on Gaussian distributions, but I will explain how it extends beyond to exponential families. And then I'll also talk about some open problems in the end. Our paper has many parts, but I would distill the main results to these. The first is an efficient estimation algorithm for general, non-diagonal Gaussians and exponential families for very general sets. We also have the first polynomial time estimation algorithm when the set S is a half space or axis-aligned box. Due to the results for general Gaussians having unknown truncation set, we have this application to linear regression with unknown truncation. For instance, let the covariance X be distributed according to some Gaussian distribution and Y be related to X in the standard way. Now, X and Y are jointly Gaussian, and suppose these X and Y pairs are jointly truncated to some set S star. Because of our results for general Gaussians with unknown truncation, we can now solve linear regression problem with this notion of unknown truncation. We want to emphasize that because the prior work required diagonal Gaussians, and since this joint distribution of X and Y does not have a diagonal covariance matrix, we're able to solve this type of linear regression problem, which had not been solved before. Pictorially, what this looks like is in FOCS 2019, Manolis and Zampetakis initiated the study of statistical estimation with unknown truncation, and their results applied to these Gaussians with diagonal covariance matrices. We are able to generalize this now to Gaussians with arbitrary covariance matrices. And furthermore, we have a polynomial time algorithm when S is a half space or axis-aligned box. Furthermore, our approach does not depend on Hermite polynomials, which the 2019 paper relied on. And these Hermite polynomials form an orthonormal basis under Gaussian measure. Because we do not rely on this Hermite polynomial construction, we're able to generalize this now to exponential families. In this case, let P be the minimum degree of polynomials which can approximate the indicator of the set S star in the L2 norm with respect to the true data generating distribution. For general sets which can be approximated by these polynomials, degree P polynomials that is, we have this d to the poly P over epsilon time algorithm for these very general sets. And in fact, for Gaussian distributions, this P and the Gaussian surface area of the set are related to each other. And then we have a polynomial time algorithm when S is an axis-aligned box. One might notice that on the bottom right, we do not have half spaces. So an open question would be how to design polynomial time algorithms for half spaces for distributions beyond Gaussian. Now I'll give a high-level overview of the proof. The main challenge here comes from the fact that S star is unknown. Our approach factorizes into two modular steps. First, we learn an approximation S to S star. Now, given access to this approximation to S star, we then learn the parameter. There are some subtleties here where recall that the apparent data given to us is drawn from the distribution truncated to S star, not S. So if one were to naively replace the log likelihood with S wherever S star shows up, this objective is no longer well defined in the cases where a point belongs to one set and not the other. Instead, we come up with a new optimization program that we call the perturbed log likelihood. This is no longer a likelihood objective. And in fact, the optimizer of this program is not necessarily equal to theta star anymore. However, we will show that the solution to this is close enough to theta star. On the other hand, in trying to learn an approximation to S star, the challenge here comes from the fact that we only have positive samples. If you were to view this as a binary classification problem, we only have points that are definitely inside our hypothesis set. On the other hand, we do not have any examples of things that definitely do not lie in S star. Due to a hardness result in 1987, almost no hypothesis classes can be learned from just positive samples. However, we are going to be able to make use of additional information to kind of get around this hardness result. To get polynomial time algorithms now, we develop a new algorithm to learn half spaces from just positive samples under Gaussian distribution. And on the other hand, axis-aligned boxes and a few other restricted classes, which are exceptions to this hardness result, there are polynomial time algorithms to learn just from positive samples. It's been known that if you have additional information, such as unlabeled samples from your data generating distribution, you're able to solve this problem. But in our case, the unlabeled distribution would just be the non-truncated distribution parameterized by theta star, which we're trying to learn in the first place. Instead, we're going to be able to generate unlabeled samples from a distribution close to our data generating distribution, given the data at hand. Now what we'll have are the positive examples from the apparent data given to us that we know are truncated to S star, and we'll label all these unlabeled samples from a distribution close to our data generating distribution as negatives. And in doing so, we'll reduce this problem of learning from positive samples to agnostic learning with respect to this mixture distribution. Now, to efficiently solve this agnostic learning problem, we will go down 2 branches. For this d to the poly p over epsilon time algorithm, we will be using this L1 regression algorithm by Kalai and others from FOCS 2005. While many agnostic learning problems place structural assumptions on the hypothesis class or the data generating distribution, the L1 regression algorithm is very general in the sense that we just need a degree p polynomial which can approximate the indicator of the set S in this L2 norm sense. And the underlying distribution just needs to be log concave. The issue in our setting is that although even if both the distribution of positive samples and unlabeled samples are each individually log concave, their mixture may no longer be log concave. Instead, we show that if there is a bridge distribution which is close in chi-square individually to both the positive sample distribution and the unlabeled sample distribution, then their mixture is going to be close to this bridge distribution. And this will be enough for us to use this L1 regression algorithm. For our polynomial time algorithms, we develop a new method for learning half spaces under Gaussian distributions. In this case, we use information about the third moments and its relation to the components of the normal vector of the half space. On the other hand, for axis-aligned rectangles, there exist methods for learning with only positive examples, and this is one of the exceptions to Natarajan's hardness result from 1987. At this point, we've learned an approximation to our truncation set S star, and now we need to recover the parameter. Normally, maximizing the log likelihood is a standard method for our parameter inference. So if we knew S star exactly, this would be the population likelihood objective that we'd want to maximize. But the issue is that we don't have access to S star, but to S, although it is close to S star. In this case, we'll maximize a slightly different optimization program that we call this perturbed log likelihood function, and the differences are highlighted here in red. Even though this perturbed log likelihood function is no longer a real likelihood function, this objective is still concave, and some theta hat will maximize it, and we'll show that it will maximize it uniquely over some domain. In general, this theta hat is not equal to theta star, but we can show that it's close enough. So how do we do this? We'll first construct a domain over which our PLL objective is strongly concave. It turns out that if we solve the maximum likelihood estimation with our given data as if there were no truncation, this parameter that solves this moment matching problem has a bounded distance to theta star in this way. So for instance, if you were to have data from our truncated Gaussian, theta naught would be initialized using the empirical mean and covariance of the truncated data that you have on hand. Because of this parameter distance bound, if we construct this neighborhood around theta naught, this will contain theta star, and furthermore, we can show that over this domain, our PLL is strongly concave, or its negation is strongly convex. Because of this, we'll use strong convexity to transfer likelihood objective distances to parameter distances, and we can show that the gradient has small norm at theta star here. Now, if we recover an approximate solution to PLL using the projected stochastic gradient descent that exists for the known truncation methods, this theta tilde will be close to theta star. In summary, our contributions are the following. We have the first algorithm for estimating a class of exponential family distributions, including general Gaussians, truncated to an unknown set. This also gives the first algorithm for linear regression with unknown truncation with Gaussian features in the setting that I described earlier. We also have the first polynomial time algorithm for estimating parameters of a class of exponential family distributions, including arbitrary Gaussians, when the survival set is from a restricted class, for instance, half spaces and axis-aligned rectangles. And of independent interest, we have a reduction from pack learning with positive and label samples to pack learning with positive and negative samples that is robust to certain covariance shifts. Some open problems in this truncated statistics space would be first, that open problem that I mentioned at the beginning of the talk of having polynomial time algorithms for half spaces under different distributions other than Gaussians. In addition, it'd be nice to have polynomial time algorithms for other restricted classes of S, for instance, intersections of two half spaces beyond what's presented here, and, for instance, linear regression with unknown truncation with non-Gaussian marginals. Thank you for listening to my talk, and we hope you'll check out our paper on arXiv under the same name.